Okay, here's problem number 2 from homework 5, and I'll do this as an example problem here. It says, consider a TDM multiplexer used to create a T1 signal. Suppose that one of the 24 PCM and tributaries was sampled a little bit slower than the others with an average sampling rate of 7950 samples per second. The normal rate is 8,000 samples per second. Assuming 8-bit PCM sampling, calculate the bit rate of this tributary. How often will a bit slip occur when multiplexing this tributary with the others, which are all assumed to be perfect? Give your answer in units of bits, and also in part C to give the answer in units of seconds. So this is a fairly straightforward application of the equations that were given, and what I'll do is I'll simply write that the base data rate, I'll call it R0, is 8,000 samples per second, and that the rate for this one funny tributary, this one slow tributary, R1, is going to be 7950 samples per second. Okay, and for part A, it asks for the bit rate of this tributary. And so for part A, I'm going to say that the bit rate R, RB, let's call it, is R1 in samples per second times LS, let's call it, the length of a sample. And so this is going to be 7950 samples per second times 8 bits per sample. You can label this variable whatever you want. I called it LS for the length of the sample. And this is going to give us something a little bit less than 64 kilobits per second. The normal would be 8,000 times 8. And this yields 63.6 kilobits per second, or 63.6 thousand when you do the multiplication. And part B and C ask for bit slips. And the equation I gave you was that a bit slip occurs every n bits, where n, or 1 over n, is equal to delta r over r, which is the fractional error in the data rates, or in the sampling rates. And I can write then that delta r is 50, or 8,000, minus 7950 divided by 8,000. You could put 7950 in the denominator if you want. It doesn't change the answer much, which is 50 8,000ths, or 1 part in 160. And so this implies that n is equal to 160 bits. 160 every 160 bits. Okay, we're going to have a bit slip, okay, as these signals are multiplexed together. I could have put 64 kilobits per second and 63.6 into this equation if I wanted. It yields the same thing, 1 part in 160. So I could say that n is 1. So I'm going to use n in the units of bits here. Okay, so for part C, I need to know the time of the slip, how often a slip occurs in time, not how often a slip occurs in bits. And I'm going to do that by saying that the t for a slip is equal to n times the period of a bit. So it takes 160 bit periods to get a bit slip. And the bit period is nominally, I'm going to use the bit period as 1/64,000th of a second, so that so that T naught is 8,000 times 8, which is 64 kilobits per second. And I'm going to use this as the bit period. Okay, I'm sorry, that's the bit rate, and that's 1 over the bit period. And so the bit period is 1/64,000th. Okay, and so I have 160 is n, and 64,000 is, and 1/64,000th is t-bit. And so I get, when you multiply this out, 2.5 milliseconds. Okay, so I hope that helps you with problem number 2. So we have a bit slip occurring 1 every 160 bits, and the bit slip occurring once every 2.5 milliseconds. Thanks.